you have a decreasing sequence of
triangular regions. These are all compact sets, right? You have a decreasing sequence of compact sets. So what about the size of these? So what about the length of T itself? What is the relation between the length of T and the length of Tn? At every stage, length is halved, right? So T1 is half of length of T, T2 will be 1 by 2 square length of T, and so on. So 1 over the other way. So the size of these triangles decrease to 0, right? So you have the Cantor intersection theorem, remember? If you have a decreasing sequence of compact sets whose diameters go to 0, then the intersection is a single point, right? I mean, without the condition of the diameter, the intersection is non-empty, but if it goes to 0, then the intersection is a single point. So Cantor a single point Z0, let's say. So let's see what happens at Z0. So Z0 is in every triangle there. So it is in the domain of holomorphy of the function, domain of analyticity. So F is analytic at Z0. So you can write f of z, f of Z0 plus f prime Z0 into Z minus Z0 plus the remainder, right, in a neighborhood of Z0. R is the remainder term, R over mod Z minus Z0 goes to 0 as usual, right? Say you take a disk, you can take a closed disk by going to a smaller disk there, okay? So see, but then you see these triangular regions all shrink to 0. So any neighborhood of Z0 will contain after some stage all the triangles, right? So for large enough n, Tn will be contained in this disk for all sufficiently large n. So you don't have to integrate over R, you can integrate over n, Tn, right? Tn lies inside this. So this holds in Tn, inside Tn, that is in delta n, okay? So Tn disk. Let us give some name there. So dr. Just to, so Tn is contained in dr for all sufficiently large n. Because the Tn shrink to Z0. So this therefore is valid inside Tn. So you can integrate over Tn. For integral over Tn of fz is integral over Tn of fz naught z plus f prime z naught What about this term? Zero, right? Constant. You are integrating constant along a closed curve. Is just power of z. So these are all zero. So you are essentially left with the remainder term, integral of the remainder term. So you are left with the task of proving that the integral of the remainder term is 0. Right? So basically, therefore, we have to estimate the integral of the remainder term on Tn. Right? What is the property of the remainder term? As z goes to z0. So in particular, this quotient remains bounded on Tn. So we can write that this is less than or equal to, you call this so maximum of over Tn of z naught. So R you write as R over z minus z naught times z minus z naught. So this into mod z minus z naught. Right? So z naught is inside Tn. Z is, we are integrating on Tn. So z lies on Tn. Okay, so we have z is some, yeah, z is some point here, z naught is here. So the length is of course smaller than the diameter of the triangle, which in turn is less than the length of the triangle. Okay, so what will you get? The bond. So this is a bond for R over z minus z naught. So you have another z minus z naught, which is bounded by the length of the triangle. Okay, and then remember the estimate for an integral, maximum of the integrand times the length of the curve. So the integrand itself is bounded by this times length of Tn. So there is another length of Tn coming in, right? So I mean, here you get first, if you want, diameter of Tn, which in turn is less than length of Tn, times length of Tn. Is this okay? R so I am writing R like this. So bound for this is this. Bound for this is this. Times the length. So this is whole thing is the bound for the integrand. Right? Bound for R. Times the length of the integral there. But what about this? Of course, we have some estimate for Tn in terms of length of T, right? We'll come to that. But what about this itself? As n grows large, Tn is going to shrink to T naught. Right? So this is the maximum of Tn. So this is the whole thing is going to shrink to 0. Right? So if you denote this by something, whatever, mu n or something, mu n is the maximum of this or that, then mu n because the triangle shrink to single point that now. So what is the estimate therefore? Mu n length of Tn square. So we have to relate it with T. What we want is T, right? How are these related? How is so what you have therefore is so integral over Tn is bounded by this. But what is the relation between integral over Tn and integral over T? At every stage you have 1/4, right? So what is the relation between integral over what is the relation between these two? How did we choose our Tn? Integral over T1 is greater than or equal to 1/4 integral over T. And then integral over T2 is greater than or equal to 1/4 integral over T1. So integral over T2 is greater than or equal to 1/4 square integral over T. Right? So integral over Tn is going to be greater than or equal to right, or you take the 4 to the n to the other side. But we have an estimate for this. So this is less than or equal to 4 power n mu n length of Tn. What is length of Tn in terms of length of T? Length of Tn is 1/2 to the n length of T. So right? Length of Tn square. That's what you have. So this 4 to the n will cancel out there, and you are going to get that length of T square times mu n. Right? Now if n is large, the right hand side is small, because I already said this. The left hand side is independent of n, and the right hand side goes to 0 as n goes to infinity. So which means the left hand side is 0. So that proves the Gauss lemma, right, or the Cauchy theorem for triangles. Right. So Gauss's paper actually appeared in 1900. Transactions of the American Mathematical Society. So for all the things that we want to do, which basically to start with is to get a power series expansion, what all you need is the formula for a disk. Okay, because power series is usually expanded in a disk, right? You have. So for that, this is going to be sufficient. From this, we can derive the Cauchy's theorem and then the Cauchy's integral formula for a disk. But the proof that we can give for a disk actually works in a more general, for more general domains. Say, for example, convex domains. You know what is convex, right? If you have 2 points in the domain, the line segment joining any 2 points lies in the domain. Or even more generally, what are called star-shaped domains. Or star-like domains. What is the shape of a star? Of course, the actual shape of a star is round. The way we see the star. Right? Forget all this. So, what is special about such a domain? It's not obviously convex, right? If you take 2 points, these 2 combus, the line segment is not going to be there in the domain. However, take this point, for example. The line segment joining this point to any other point in the domain lies in the domain. Right? Whichever point you take. So such a domain is called a star-like domain or a star-shaped domain. That means what? A domain in which there is a point, let's say Z0, such that for any other Z in the domain, the line segment joining Z0 and Z lies inside the domain. Right? So line segment, let me write like this, okay? This stands for the line segment joining Z0 and Z. So this is more general than convex domains. For a convex domain or a star-shaped domain. Oh, we can use a convenient terminology so that, so let us call such a Z naught as a, I mean, just to write something conveniently, star center. Just for easy reference, okay? Convex will do for us, but so we don't gain anything by restricting to convex. Same, essentially same proof is going to work for this, so why not? So what is the theorem? If you have a star-shaped domain and a closed curve, not a a closed curve, which along with the interior of the curve lies in the domain. Okay, the integral of any analytic function over that closed curve is 0. Actually, we can prove what is apparently slightly stronger, namely that any analytic function in a star-shaped domain has a primitive. Once a function has a primitive, the integral along a closed curve is going to be 0, as we already mentioned, right? So omega star-shaped domain. So if F is analytic omega, then F has a primitive in omega, and in particular together with the interior contained in C. Both the curve and the interior of the curve lie inside omega. So take the star center. So for any z, consider the triangle formed by Z0, A and Z. Z0 is the star center, A is some fixed point, Z is an arbitrary variable point. So apply the theorem, Cauchy's theorem for triangles to this triangle, right? So in fact, we can even specify what the function g is going to be. So, so what do we want to do? To find g such that g prime z equal to fz for all z. Right? This is what we want. So apply Cauchy's theorem to the triangle T formed by Z0, A and Z. What is the conclusion? We conclude that integral over T 0 So this is integral over the three segments Z0 A, AZ and ZZ0. Of f zeta this can be a degenerate triangle, in which case it's just a line. So for example, if z lies here, we'll like this and then go back, so we'll get 0 in any case. Okay? So I mean the thing holds still when even if the triangle is a degenerate triangle. So this is generic case what we are writing. This you can take to the other side. Z0 Z becomes the opposite orientation, right? It's integral Z0 Z Okay? So this term I am taking to the other side. I am changing the orientation of this. That's all. So what do you have now? So this is so z is any variable point in omega. So if you call this function as z, gz, so Z0 is the star center, so it's fixed. So for any other point, look at the integral over the line segment joining Z0. So here is where your things come in, right? This always lies in the domain because the domain is star shaped and Z0 is the star center. By the way, there is some question to be asked even before that. A and Z are some point, 2 points in the domain. So why should the line segment AZ lie in the domain? Right? So what is the answer? Of course, there is no problem with this and that, because Z0 is the star center. Line segment joining Z0 to any other point lies in the domain. So this lies in the domain, this lies in the domain. What about this term? The line segment AZ. See, what we are trying to show here is that G is a required function. You want to show that G prime A is equal to f of A. You want to show that G is differentiable at A and G prime A is nothing but f of A. So what you want is to look at only a neighborhood of A. You want to check differentiability at A. You need to check, you need to only look at a neighborhood of A, right? A is a point in the domain. The domain is open. So some neighborhood of A is going to be, so let us draw a picture, okay? So this is your, whatever, star-shaped domain or what, okay? Round about that, that's going to be convex, so. Okay. This is your domain. So A is some point there, and so some neighborhood of A is going to be inside your domain omega. You are interested only in point Z which are close to A, in a neighborhood of A. So we are going to take only Z here. Okay. So in which case, there is no problem with this. There is going to be inside that disk, and therefore inside your omega. Okay? So you have to observe that before writing this. For Z close to A, the line segment AZ will lie inside omega, and therefore this makes sense. Okay? So you can close to A, apply. Close means sufficiently close. Sufficiently close means inside omega. So note here that for Z close to A, AZ will be contained in omega. Okay now? So now everything is fine. No problem with any of this. So if you call this as GZ, so now G is defined only in that neighborhood, right? G is not defined on the whole of omega. So G is defined in a neighborhood of A. So let us see. So what does this give you? This is GZ. This is G of A, right? So what is z minus g of a over z minus a minus f of a? This is what we are interested in, right? We want to show that limit of this is this. So what is this? One over z minus a into right? You can take this inside. If you are integrating a constant on a line segment, what are you going to get? I mean, not a to z, but the line segment a to z. The final point minus the initial point, right? That means z minus a. Just cancel off with this. Okay? Just give you fa there. So what is the estimate for this? The maximum for the integrand, right, times the length of curve. Length is mod z minus a. So what do you get? Mod z minus a of course cancels off, and what remains is maximum of mod f zeta minus a on z minus a on the line segment az. So what happens to this as z goes to a? So this goes off. So f is analytic. In particular, it is continuous, uniformly continuous on that segment. So this goes to 0 as so Cauchy's theorem for convex domains, or more generally star-shaped domains, is an easy consequence of Cauchy's theorem for triangles. So in particular, we have Cauchy's theorem for disks. Disks are our convex sets. So Cauchy's theorem holds for convex sets. So in particular, you have Cauchy's theorem for disks. That means what? If your function is analytic in a disk, and you take any closed curve inside the disk, then integral of that of fz along that closed curve is 0, right? So if you have a disk D and a curve inside this, then let us now give a small twist to Cauchy's theorem for triangles. So what does it say? If you have a function analytic in some domain, and you have a triangle which along with its interior is contained in the domain, then integral of any analytic function along that triangle is 0. Okay? So in particular, all the sides and all the vertices of the triangle lie in a domain where the function is analytic. Right? We can tweak this a little and allow one of the vertices to lie outside the domain of analyticity. Meaning, or improved version of Gustaf's lemma if you want. If you're not familiar with the word tweak, don't worry. So if f is analytic let me just write this, forget the brackets, okay? So I'm omitting a point in omega. But it is continuous on omega. Because you want to talk about the integral on the triangle. So on the triangle, the function should be continuous. So then for any triangle T with a vertex at Z0. See, for all the vertices lie in omega, then fine. I mean, there's nothing new. It's already there in the. So even if one of the vertices is in that omitted point, still the integral is 0. And of course, the other things are the same, right? Other points of T and the interior of T are all inside omega. Those conditions are still there. With, of course, other points of T, T minus Z0, omega, and interior of T is inside omega. The other conditions are all still there. Only one point, this can be reduced to the untweaked case, so to say. Suppose this is Z0. Okay. So one of the vertices is Z0. So what you do is you take, so you have two sides of the triangle with vertex at Z0. So on each of those you take point each on each of them close to Z0. Right? Let's say Z1, Z2. And okay, so this is no longer a triangle, so join one of these to the other vertex. Okay? We need triangle, so what do you get now? What is given is, what you want is to evaluate the integral on the whole triangle. Okay. So integral on the whole triangle is the sum of integrals over these three triangles. What about, forget the small triangle, what about the other two triangles? The integral is already 0 by the original Gursa, right? So you have to only look at the small triangle. But what is the problem with the small triangles? Triangle is small, so you can make it as small as you want. So the integral over that small triangle is going to be bounded by whatever the maximum of fz on that triangle times the length of the triangle. Maximum of f on that triangle is in turn bounded by maximum of f on the whole triangle. Right? F is continuous on the whole triangle, bigger triangle. So maximum of f over the bigger triangle, mod f over the bigger triangle, times the length of a small triangle, which you can make as small as you want. Right? By taking Z1 and Z2 arbitrarily close to Z0. That's all. Right? So you can write down the proof. Writing down is as important as understanding. Once you understand, you must be able to write. Okay? So you must, so this is a skill that you have to develop. Writing something that you know. Right? In a mathematically at least, a logical, mathematical sequence of steps. So how do you write in this case? What is the proof? How do you go about? So you write all these in words. I have drawn the picture. You write those things in words. So in other words, Z0 is already given to a vertex of T. Let Z1, Z2 be the other two vertices. I'm sorry, no. We are taking Z1, Z2 to be this. So this T. So you take point Z1. Maybe it's easier to give some names, okay? Maybe Z1, Z2 you can give for this. You can give some other names for this, right? So that whatever W1, W2 or whatever you want. So Z0, Z1, Z2 is the given triangle T. Take point zeta 1 on Z0, Z1 and zeta 2 on Z0, Z2. You can write as you say. Come on, start writing. So denote the given triangle T by Z0, Z1, Z2. Or let these be the vertices of the triangle T. So if you want, you can start with an epsilon, right? So that you can make things precise. So let epsilon be greater than 0. Okay. Choose points zeta 1 on Z0, Z1 and zeta 2 on Z0, Z2, so that the length of the triangle Z0, Z1, Z2 is less than epsilon. Okay? So label these triangles if you like. So this is T1, T2, T3, integral over T of Fz. Right, integral over T is the sum of the integral over this divided triangles. And then what happens? So what is the next step? This sum is actually equal to integral over T1. Because what? Integral over T2 and integral over T3 are 0 by the original Gauss lemma. Then what? Estimate now. Integral over T right? And the integral over T1 is less than or equal to maximum over T1 of mod Fz times length of T1, which in turn is less than or equal to length of the maximum over T of mod Fz times epsilon, right? The length of T1 you have started with, have you written that? So choose those points so that the length of T1 is less than epsilon. So you get that the whole thing is less than length of T times epsilon. After, of course, a couple of steps here. So epsilon is arbitrary, and therefore left hand side is 0. Then, so what is the advantage now? So from this improved version of Gauss's lemma, you get a improved version of Cauchy's theorem for star-shaped domains. So here you assume analyticity in the whole of omega. So it's enough if you assume. So what did we use? We used a triangle with one of the vertices at Z0, right? Z0 AZ. So we can exclude Z0 from the domain of analyticity, right? with, of course, Z naught is mentioned, not mentioned in the statement here, so let's, with star center, Z naught. And continuous on omega. Then you don't assume analyticity at omega, but at Z naught, but assume continuity, okay? Because you have to integrate. What changes do you need in the proof? You don't need any change, right? Because we took a triangle with Z naught as a vertex. So even if Z naught is a point of is not a point of analyticity, it still holds by the improved Gauss lemma. So this is still fine. So no change is necessary in the proof. So the same proof goes through, except that you invoke the new Gauss lemma instead of the old one. That's all. So now comes the all important take any point and choose a disk, closed disk around Z naught, around zeta contained in. So if the closed disk is contained in omega, then let us call it C. I think we used some notation earlier, right? So C zeta R. Circle with center zeta, radius R. So we are going to apply only for a disk, Cauchy's theorem only for a disk, although we proved it for star shaped and so on. All that you need is disk. Okay, let us do some. That is zeta and this is R and so on. So take a slightly larger disk around that. You want to apply Cauchy's theorem for a disk. So you want to find a suitable function which is analytic on that slightly larger disk, okay, so that this circle will lie inside that disk. You can apply Cauchy's theorem for that circle there. Integral over of a suitable function over this circle CR is 0, right? What is that suitable function? Define say f of z or g of z, whatever it is. A natural choice. So what can you say about this function f? Capital F is analytic everywhere except possibly at zeta. What happens at zeta? It's continuous, right? Because the limit of this is this. Improved Cauchy theorem for the disk, let's say, right? So you have a function which is, so look at the statement of that theorem. You have a function which is analytic in omega except at some point, in this case zeta, maybe z naught earlier, and also continuous at that point also. Then what is the conclusion? Integral of the function is 0 along any closed curve, right? So f is analytic in omega minus zeta, and the continuous on omega. So by the tweaked or improved Cauchy theorem, for a disk so what is the disk that you are looking at? A slightly smaller disk, right? So give the name for the disk mod z minus zeta less than something r, let us say. This r is bigger than the r here, and such that mod z minus zeta less than or equal to r. This is also lies in maybe the better way to write it. So you denote this disk by something, and then by the tweak Cauchy theorem for that disk, you have what do we get? Integral over whatever we call that c zeta r of fz dz is 0. But what is this? So on this circle, this doesn't come into the picture, only this part. So fz over z minus zeta dz minus what? F of zeta. just splitting into two parts, that's all. What is this? So this is, keep it as it is. But what about the second integral? F zeta you pull out, and then integral dz over z minus zeta. What is the value of that? 2 pi I. That's all. F of zeta huh? So that's the Cauchy formula for a disk. The value at the center, right? That's what it gives. Is the average of the value of the function on the circle. If you write this, write z as zeta plus re for it. Okay, we'll come write that anyway. What is called the mean value property. Just rewrite this in terms of t, that's all. So that gives the integral formula. You will see that once you have this formula, the power series expansion is almost immediate, right? So that's our next thing. So we'll easily get the power series expansion for fz around each point in the domain. Okay, so that we'll do in the next class.